Alright, so today we're going to look at 3.4. 3.4 is on concavity and second derivative test. So first off, what is concavity? Concavity is where the graph is curving upward or curving downward. So by definition of concavity, let f be differentiable on an open interval I. The graph of f is concave up on I if f prime is increasing on the interval and concave downward if it is decreasing on that interval. So this is what this looks like here. All right. All right, so if it's concave up, f prime is increasing. It would look something like that. And all of your tangent lines for this would be below the curve. Below the function, then it would be concave up and f prime is increasing. Same thing in the other direction, concave down. If we look something like this, at any point on this, the tangent line is above it, and it is concave down, and f prime is decreasing. So to do a test for concavity, we have f prime be a function whose second derivative exists. So if f double prime is greater than 0, then the graph is concave up. If f double prime is less than 0 or negative, then the graph of it would be concave down for that interval. So that's our test for concavity. So let's put that to test now. So determining concavity, you want to determine the open intervals on which the graph of the function is concave up or concave down. So we're going to take this function here, f of x equals 6 over x squared plus 3. So first off, let's just make this something that we can differentiate a little bit easier. Make it f of x equals 6 times x squared plus 3, and we'll take it to the negative 1 power. So all I did was just create this into a single thing, just because it's a little easier to work with this way. Go ahead and let's find the derivative of this. So f prime of x equal to negative 6 x squared plus 3 to the negative 2. All I did was use u substitution here. And then inside the parentheses would be 2x. All right, so that's what I'm looking at here. So let's just rewrite this again with positive exponents. I have negative 12x over x squared plus 3, the second power. So that would be the first derivative of this guy. Now, I can do something similar for this one, but now since you'd like to do something similar, but now because I have an x on top, now I have to do the quotient rule for this one. So let's find f double prime. So f double prime of x, we have low d high minus high d low over the square of what's below. So we're going to have x squared plus 3 to the second times negative 12 minus negative 12x times 2, and then x squared plus 3 times 2x all over that squared, x squared plus 3 quantity squared. All right, and then that's going to be 36 x squared minus 1 over x squared plus 3 to the third. And I get that just by simplifying a little bit. I just saved the time by not showing the simplification steps here. Now, since f double prime of x is equal to 0, when x is plus or minus 1, so this would be equal to 0 when x is plus or minus 1. So that would be our points here that's going to mess this up for us here. All right, that's going to make it 0 because 1 or negative 1 on top is going to give us a 0 on top of the fraction. All right, so now we want to test the intervals. So our intervals, kind of like we did before, critical values interval, our test value, Now we're looking at the sign of f double prime, and then we're going to have a conclusion again. So from negative infinity to -1, we're going to have -1, +1, and then we're going to have 1 to infinity. All right, so let's just use our test values. Let's use x equals -2. We'll use x equals 0. We'll use x equals 2. All right, so f double prime of -2 is going to be greater than 0. Therefore, it is concave up. When we put a 0 in, f double prime of 0 is going to be less than 0. So therefore, it's concave down. And then lastly, when we put a 2 in, and we're putting this into the second derivative, we're putting it into this guy right here, that is going to be greater than 0. So therefore, this is going to be concave up. All right, so that means from infinity to -1, it's going to look something like this. Concave down looks something like this. Concave up looks something like that. All right, and what we're doing, we're building this to a point where we're going to be able to graph these guys by using all these tests. All right, let's do it again here for another one. It's just a different function, x squared plus 1, x squared minus 4. All right, this guy we're going to have to differentiate twice again. So let's go. F prime of x is going to be low d high minus high d low. So x squared minus 4. And this will be 2x minus high x squared plus 1 d low will be 2x as well. And it's all going to be over x squared minus 4 20 squared. Simplify that a little bit. F prime of x is going to be negative 10x over x squared minus 4 20 squared. All right, do it again. F double prime. All right, so now we're looking at low, should be x squared minus 4 quantity squared d high, so it's negative 10 minus high d low. We have to use u substitution on the bottom. 2 x squared minus 4 times what's inside the parentheses, derivative of that, all over x squared minus 4 to the 4th power now. All right, again, save some time on simplification. We're looking at 10 times 3x squared plus 4 over x squared minus 4 to the 3rd. All right, so in this case, we can see that f double prime, there's no points that's going to make this 0 because it doesn't matter what I put in for x up top. But so the top doesn't really help us, but if I look at the bottom, when x equals plus or minus 2, that's going to make this not continuous. All right, so that's going to be our two values that we use here. Okay, interval, test value, sign of f double prime, and then the conclusion. So we're looking at negative infinity, -2, we're looking at -2 to 2, and we're looking at 2 to infinity. Alright, so I'm just going to use x is -3 for this one, x is 0 for this one, and x is 3 again there. Alright, so again, I'm going to plug it into my double prime, my second derivative. So f double prime and -3 is greater than 0, so that's concave up. If I put I put 0 into f double prime, it's going to be less than 0, so it's concave down. And if I have f double prime of 3, that's greater than 0, so that's concave up. All right. All right, next thing we have points of inflection. So points of inflection is going to be basically where our graph changes from concave up to concave down. So here's the definition. The f be a function that's continuous on an open interval. Let c be a point in the interval. If the graph of a tangent line at this point, then the point is a point of inflection of the graph. Concavity changes upward to downward or downward to upward at that point. So theorem 3.8 says for our points of inflection, if c of f of c is a point of inflection of the graph of f, then either f double prime of c equals 0 or f double prime does not exist at that point. So basically all these points that we've been finding are going to be what are points of inflection. All right, so to find the point of inflection, we're going to do the same thing. We want to differentiate this twice and check out the intervals. So again, we're not really changing what we're doing. We're still checking for concavity here. All right, so 5f of x equals x to the fourth minus 4x to the third. F prime of x is going to be 4x to the third minus 12x squared. That's an easy one to differentiate. And then we'll go f double prime then. So f double prime of x is going to be 12x squared minus 24x. And let's go ahead and factor this guy. So I can factor out a 12x and leave it x minus 2. So this one's easier to see what's going on here. All right, with that. So set it equal to 0. We can see that we have points of inflection. They occur at x equals 0, x equals 2. So that's going to be what sets our intervals again. All right, interval, test value, sine of f double prime, and then whatever we decide there. So we're going to have negative infinity to 0. We're going to have 0 to 2, and we're going to have 2 to infinity. All right, so let's use the points. X is -1. Here we put in x is 1. Here we'll put, I don't know, let's go 3. All right, so put this stuff into f double prime. So put it into our function right here. F double prime of -1 be greater than 0. So it's concave up. Next one, f double prime of 1 is less than 0. So that's concave down. And then lastly, f double prime of 3 will be greater than 0. So it's concave up. All right, so that's really no different than what we did on the previous ones. Last thing we want to look at for this one is just going to be what's called second derivative test. So in addition to a testing for concavity, the second derivative test can be used to perform a simple test for relative maxima and minima. Theorem 3.9 gives us a second derivative test. It says let a function such that f prime of x equals 0 and the second derivative of f exists on an open interval containing c. F double prime is greater than 0, there's a relative minimum. If f double prime of c is less than 0, then there's a maximum. And if the test fails, you may have a relative max or relative min or neither. In such cases, you would use the first derivative test. All right, so we use the same type of things we've been doing here for the last couple. So we have f of x is negative 3, x to the fifth, plus 5x to the third. So let's check out f prime of x. So f prime of x, I'm going to have negative 15 x to the fourth plus 15x squared. And I can factor that, set it equal to 0 and factor it. So I'm going to have negative 15x squared I can pull out, leave me with 1 minus x squared. I just rewrote the order on that one. If I set that equal to 0, I find that x equals 0 at negative 1, 0, and 1 for this case. Add plus and minus 1 from this guy, and 0 from here. All right, so those are going to be our critical numbers, just like we talked about before. All right, so now we can use our f double prime. So we're going to go f double prime of this guy up here. That's going to give us negative 60 x to the third plus 30x. Factor 30 out of both of those, and that's going to leave me with negative 2x to the third plus x. All right, so now I just take that, I'm going to apply the second derivative test. So in this case, I'm going to plug in points. Okay, I'm going to plug in the point negative 1, negative 2. Okay, I'm going to plug in the point 1, 2, and I'm going to plug in the point 0, 0. All right, so now if I look at the sign of f double prime, I'll be able to know whether this is a relative min or a relative max. So f double prime of negative 1 is greater than 0, therefore it's going to be a relative min. Second one, f double prime of 1, I'm just plugging in my x values here. This guy's going to be less than 0, so it's a relative max. And then lastly, put in 0, 0, so f double prime is 0. That's going to be actually equal to 0. So here, the test fails. All right, because the second derivative fails at 0, 0, we can use the first derivative test, and you can see that f increases to the left and to the right of x equals 0. So this is just what we did in the last lesson. So it would increase on both sides of 0. Therefore, it's not a minimum, and it's also not a maximum. And actually, what this graph would look like roughly, so you can see what we're talking about. It's going to come down till it hits 1. Here's 1 and 1. Then it's going to change concavity here, change concavity, and then change concavity again. It's going to look sort of like this. Okay, and here's those critical points we just found right there. All right, so that would be lesson 3, 4.